Let's continue our discussion about part 2. I will show you analogies between Schrödinger's equation and Maxwell equation. Looks very interesting. Okay, analogies between Schrödinger and Maxwell equation. First, let's have a look at time-independent Schrödinger equation. Can be written into this form. Okay, in terms of G component, one-dimensional, time-independent. Okay, Maxwell equation for a TE waveguide mode also in this way, and omega, and quite similar, right? This is wave function. This is BZ. Of course, you can express in terms of TMO, quite similar. And for this case, for a waveguide, and for this one, E2m. M is the mass of the charge of the particle, and H bar is shown here. V is the potential barrier height. Omega C just plays a role similar to V. Omega C squared, cutoff frequency squared. Okay, similar. And energy of the particle can be replaced with kz squared. Just like this part is kz squared. Okay, what else? Anything else? Yeah, we have more. Let me show you. Transmission, reflection coefficients, probability and energy velocities, and group delay phase velocity. Quite similar. Let me show you step by step. First, let's have a look at a transmission for a rectangular potential barrier. Okay, transmission of a potential barrier. And for quantum mechanics, energy is less than V. Quantum mechanics, transmission coefficient T, 1/T is shown here. And kappa squared is happen to be 2mv minus E over h bar squared. By analogy, the transmission parameter of an electromagnetic wave can be expressed as this one. Okay, just believe me, the derivation is correct. 1/T, 1 plus 1/4. Coefficient the same. Sinh the same. Kappa, similar. Okay, looks similar, right? That's transmission coefficient. Probability and energy velocity. For quantum mechanics, probability velocity is defined as J flux divided by wave number squared. And for electromagnetic energy velocity is defined as Poynting vector divided by energy density. This Poynting vector less energy density. Okay, so the result will be this part, the same. This part, the same. They just differ in here, leading terms, but the behavior looks similar. So when the omega is less than the cutoff, just similar to quantum mechanics, energy is less than the potential high. Okay, so can we use EM wave to study a long-standing debate in quantum mechanics? That is the tunneling time. The tunneling time. We can study the tunneling time. Okay, so the second summary. Superluminal effect is common to many wave phenomena, not surprise. The matter wave and EM wave share many common characteristics. Okay, so let's, the moment of truth, put the idea to the test in a three-dimensional electromagnetic systems. Let's test this idea. So now let's have a look at model analysis. effect of higher order modes on tunneling characteristics. That will be published 15 years ago. Okay, so first let's look at this one. We have a waveguide system, 3-section waveguide. The first for TE10 mode, fundamental mode, epsilon r mu r equals 1 for all regions. These 3 regions. And so K1 in these regions is shown here. In these regions is shown here. Okay? And so this is a potential well because cutoff is low. And this is potential barrier because cutoff will be high. So like this one, potential well for this one, potential barrier for this one. And B is we can simulate with an effective medium. We can put medium epsilon r inside for region 2, and the cutoff can be changed. Okay, cutoff can be increased or decreased, depends on relative dielectric constant. Okay, so we have 2 approaches. The first approach, A, is using the oversized waveguide or undersized waveguide. Oversized waveguide for potential well, undersized waveguide for potential barrier. And we can also use material inside with same cross section. Just put material in this region. Okay, so ideally, it's just like incident wave, reflected wave for potential well, transmitted wave, reflected wave, and transmitted wave. We are going to solve this one with boundary condition. Easy, step by step. And for potential well, it's incident wave, reflected wave. And here is exponential growing wave. Here is a decaying wave. There is growing wave, decaying wave inside. And D is a tunneling signal, reduced to a one-dimensional case, potential-like diagram. Okay, so this is for microwave, for electromagnetic wave. Let's have a look at this result. The coefficient D is related with transmission amplitude for 2 systems. For waveguide system, oversized waveguide, undersized waveguide looks similar but not exactly the same. The theory solid, a red solid line. The simulation, or you can simulation experiment, simulated experiment looks similar for this case, but still different. Still difference. For this case, cutoff frequency for this section 2.08, but here is much higher, much slower. So not disagree. And here cutoff is increased a lot, so wave cannot propagate. So in this region, correct, but in this region, incorrect. But consider material inside with uniform cross section. Epsilon r greater than 1 looks like the waveguide width increased, broadened. Okay, and epsilon r less than 1, the waveguide width narrowed. Exactly the same. Theory and HFX simulation, the same. So what's going on? It disagrees here. Why? Why for geometry, change the geometry, disagree, change the material, agrees well. What happened here? What happened here? Okay, let's look at this case one more time with the group velocity, group delay. Once again, tau g L divided by Vg. So delta phi in the region can be written in this form. Opposite group delay for phase-time delay. For group delay, according to the theory, it should be here. But in the experiment, in the HFSS simulation, disagree one more time. Group delay, that means group velocity disagree. And for this case, also disagree. But for material, insert material inside, agrees well, agrees very, very well, which means for this case, just like our expectation before, but for change in waveguide size, it differs. Okay, 50-50. Okay, so what shall we do? What's going on here? We should consider model effect. For this case, we should consider not just one mode, because it will excite more than one mode. It will excite because of discontinuity. More than one mode will be excited. But for this one, yes, just one mode inside. So because of the change, because of the discontinuity in geometry, more than one mode will be excited. Therefore, we should consider incident wave just one mode, but reflected wave is more than one. We have A sub n. N is to indicate number of other modes, more than one modes. Summation. Okay, instead of one mode, we have multiple modes. That's called model effect. Okay, so it's a three-dimensional problem, not just a one-dimensional problem for these two cases. Model effect should be considered. Yeah, model effect. Look at the formula. Wow. Because of discontinuity, we need to apply all the boundary conditions. For the boundary condition in this region and in this region will be different. Okay, and in a three region, input, middle region, output region, we should use all the conditions. And with when we complete wave functions and complete boundary conditions, see? As we increase the number of modes from 1, disagree, 3, better, 11, even better, 21 is good enough for transmission. For group delay, yeah, similar. Increase the mode number, the result will be agrees well. So that's for potential well. How about for potential barrier? Potential barrier, similar. As we increase the number of modes up to 9, it's good enough. And for group delay, yes, 1, 3, 9 is good enough. Okay, so that means model effect plays an important role for a three-dimensional discontinuity. To achieve a better agreement between the theory and experiment in quantum tunneling system, the model effect should be considered. We should introduce the model effect.